Swayam Prabha. Digital India. Educated India.
Okay, so let's start with the 101 of, so this I would say is probably the most important concept to understand with inferential statistics. And once you understand this, I think everything else kind of flows through normally. Okay, so this is to understand something called the sampling distribution. Okay, so what you have is, let's say you have some original distribution. So you have some random variable. You don't know what that random variable is. You're just so I've just drawn something saying this. Let's assume this is the random variable. Okay, and that's what I'm calling as the original distribution. I've drawn something that looks a little like a normal distribution or a Gaussian. You're going to soon realize it doesn't have to be. Okay, now I am going to take a sample from this random variable. Does that look like a sample? So a sample would really have fallen on that number line. It doesn't have a 2D quality. The random variable is really, this is just a density function. So I'm taking some sample that is on the number line. I've just plotted every time I got a point somewhere, I've plotted it. And like I said, it should be on the number line. Now, from this, I can calculate some mean, right? Now, if a particular outcome is a random experiment, remember we spoke about random experiments in the previous this thing? So this is a random variable. A particular outcome, therefore, is a random experiment. It's the outcome of a random experiment, correct? Now, what about the mean of these points? Is that a random experiment? So I take 5 points, and I take the mean of those points. That's going to be a number. Just like picking a point was a number that came from some distribution, because it has to come from some distribution, because when I repeat it, I'm not getting always the same value. It's not a constant, in other words. And there's a random phenomena that makes me get a different number each time with some probability, right? Now, instead, I'm going to take 5 of them. And I'm going to take the arithmetic mean of those 5. Is that a random experiment? Okay, what does it take to qualify as a random experiment? There might be some random phenomena, and I should get, conceivably, I should probabilistically, I could get a different outcome each time when it's repeated. So what is the phenomena that I'm characterizing? The mean of the 5 numbers. Now, could this be different if I do it different times? Could the mean of the 5 numbers be different if I did it different number of times? Okay, let's go to the case of dropping the ball. Fair enough. I dropped the ball once, 5.4 seconds. Second time, 5.9 seconds. Third time, 5.1. We're all very happy. We're like, this is a random experiment, right? Great. You could conceivably get different values with some likelihood function, blah, blah. Now I took those 5 and I averaged it. Now I repeat the whole process again. So all I'm left with is the average. Could I get a different average? So that number is changing not because I've changed my procedure, because of inherent randomness. So this is also a random experiment. Now I'm going to say it a slightly different way, because every time I say this, sometimes people think that inferential statistics is all about repeating experiments. It's not, right? It's a thought experiment. Just like you're not going to drop the ball, we're thinking, if we drop the ball n number of times, would we get a different average? So another way of thinking of it is, imagine if in different universes, in different places, different people were dropping it, will they all experience the same time? No. Same way, they will all need not experience the same average. So the average is also a random experiment. In which case, if that is a random experiment, what is the random variable that generated this? What is the random variable that is generating these conceptual means of 5, which are all different numbers? In completely different windows, different people following the same procedure, following the same clock, are sitting and dropping 5 of these and taking their means and taking their average. And we're realizing each of these guys are getting a different average. The individual readings are of course different, but they're all getting different averages. Now, if I take all these averages, they are again outcomes of some random variable. What is that random variable? We are going to concern ourselves with that, okay? And that is what we're going to call the distribution of sample means. So there was some original distribution, okay? And now you have something called the distribution of sample means. And I'm going to say you can get distributions of other things also. I can, for instance, be concerned about the median of those 5. I could have been concerned about the standard deviation of those 5. But all of these are some phenomena, and it's a new random variable. So I've got a new random variable, and this is what I'm going to call the distribution of sample means. Okay. So I've drawn the distribution of sample means without telling you what it should look like. This is already giving you a big kind of hint. But what should if it's a random variable, it has to have some shape. So what should the shape of this distribution be? Well, so it turns out that this shape tends to be normal thanks to something that you've all studied called central limit theorem. Remember we studied this thing back, I don't know, not in high school, but in I think second year or third year of college, that if you aggregate many random variables, usually it's referred to as the sum of many independent random variables. The result is another random variable, and that random variable tends to become normally distributed as n keeps on increasing, right? It turns out that that's one of the reasons why the normal distribution is very interesting to us. It's all thanks to this central limit theorem, right? Now, if we have time and we finish early, I have some backup slides that will try and give you some intuition of why the central limit theorem really does take place, and I'm not making it up. But you know, for now, just believe me, okay? We'll go with belief in the interest of time. So it turns out that even if the original distribution, here I've drawn an original distribution that looks kind of Gaussian, but even if it was not, that the distribution of sample means is kind of Gaussian, because the mean is nothing but the addition of 5 numbers divided by n. The divided by n is a constant. So when you're adding many random variables, you're getting a resultant random variable that is normally distributed, and you're just scaling it down or up. Okay? So the next question is, what should the mean of this distribution be? It should be the same as the original distribution, because the mean is an unbiased estimate of the true mean, right? The sample mean is an unbiased estimate of the true mean. Another way to think of this intuition is if in reality the true mean is that it takes exactly 6 seconds, right? Sometimes I drop it and it takes, so sometimes it's more, sometimes it's less, right? We're just taking the simple symmetric case. Sometimes the mean can overshoot that 6. It doesn't mean that if I take the average of 5, I'm going to get exactly 6. But it's equally likely to overshoot as well as undershoot, right? So in other words, what is the mean of rolling a 6-sided dice? So you have a 6-sided dice. What is the mean outcome of the 6-sided dice? So your sample space is 1 through 6. How would you compute the mean? Remember this summation xf of x? 1 into 1 by 6 plus 2 into 1 by 6. So what would that kind of be? 3.5, right? This is not a hard one. Come on. So you can get, the mean of rolling a 6-sided dice is 3.5. But if I roll the dice 5 times and take its average of those 5 rolls, will I always get 3.5? No. I have the distribution of sample means. But am I equally likely to overshoot the 3.5 as undershoot it? Yes. So I'm just giving you the intuition behind why the mean of the distribution of sample means, and I know that sounds convoluted, but that's the reality, right? The mean of the distribution of sample means is equal to the population mean. Okay? Now, what is its standard deviation? I'm talking about the standard deviation of the distribution of sample means. It is? It is less than original distribution. Why do you say that? the curve is like that, it looks like that. That's fair. So let's again, what I'm going to try and do is if I kind of do some demos of central limit theorem, the intuition becomes stronger. But the best way to think about it, the way I like to think about it is again to exaggerate, right? So first of all, it depends on the sample size, right? Now, what if the sample size was infinite? It was infinity. You're actually not, I want to hear those answers badly, but I just want to explain it, saying, imagine you're actually not dropping 5 at a time, you're dropping infinite at a time, and then measuring the mean. And so what were some of those answers? You get the true value, right? So in some sense, you get mu. Now, x bar is equal to mu. Now, x bar looks no longer like a distribution, right? Because if in 2 different universes, 2 different people repeated this experiments, you'll get mu because you're dropping it infinite number of times, right? So you have 2 different. So it turns out that when it's infinite, the standard deviation is close to 0, right? Now, what if your sample size was 1? What would the distribution of sample means look like if your sample size is 1? In other words, and I want to hear your answers loudly as I just explain this one more time. I'm going to take the mean of a sample. But it turns out I'm going to drop it exactly once. And so the mean of that value is that value. So what is the distribution of all those independent values? It's the same as the original distribution, right? So it turns out that if my sample size is 1, the standard deviation of the distribution of sample means is equal to sigma. So clearly, from going from 1 sample size to increasing sample size, I'm going from the original standard deviation to a standard deviation close to, going to a standard deviation of 0, right? It turns out that the exact way it is related is sigma by square root of n. This is where the sigma by square root of n comes in, okay? So this distribution, right? If this distribution was some distribution, it does not have to be normal, but it has some mean mu and some standard deviation sigma. The distribution of sample means is normal with the same mean mu, but with the standard deviation sigma by square root of n, right? So we've discussed what, so, but keep in mind, this is a funny concept to think of, right? We're talking about, for instance, when I talk about standard deviation, I'm talking about the standard deviation of the distribution of sample means, okay? Same way, can there be a distribution of sample standard deviation? Absolutely. Because in different universes or in different experiments, if you drop 5 balls and calculated the standard deviation, it's going to be different. So what is that distribution, right? Inferential statistics uses this to make the inferences, okay? We're going to use the fact that this sample mean that we've calculated is a number. But now we're even more strongly equipped. We're equipped not just with this number, but knowing that this number need not be mu, but actually this number is nothing but a random number taken out of this distribution. Does that make sense? Okay. Okay, so now I'm going to try and show you how I'm going to use this to create something called a confidence interval. Okay? Now, this is what I'm going to use. I'm going to say, look, I want to have some notion of where mu is. You've done your descriptive statistics. You've told me what x bar is. What did I give you? I gave you x's. I gave you some 10 x's. I gave you some 20 x's. You took those 10 or 20 x's and took the arithmetic mean and gave me x bar. Descriptive statistics, check, 1 point for you, okay? Now, I want you to tell me something about mu. So immediately you look back and say, okay, I don't know mu, I do know x bar, but I do know some theoretical results. I do know that x bar is nothing but a number from this distribution. So it gives me some idea of how much in front or behind mu my x bar could have been, right? So if I can look, so I know that for any value mu, I can get x bars that are before or after mu, right? If I can tell you how much x bar can deviate from mu, then for a given x bar, I can tell you how much before or after mu should have been, right? It's just the same thing. The guy in probability gave you a mu and said for any mu, your x bar can fall in front or behind by this much. The statistician immediately said, wow, that's interesting. I have an x bar in my pocket. That means I can tell you how much in front mu could have been or ahead mu could have been. Right? I'm going to say this one more time using this graph. Okay? This.
Does it not depend on the sample size?
It does, which is why you have the sigma by square root of n. So the n is the sample size. So, so what you have out here, just give me a second. So you have this mu, and you're basically saying that x bars are coming from this distribution, right? So this is what the theory guy has said. The theory guy has theorized and said, if there is some mu, then x bar is not going to fall exactly on mu. X bar is coming from some random variable, which is nothing but it's a normal distribution with mean mu and with standard deviation sigma by square root of n. Using this, I can tell you how far x bar can be ahead or behind mu. Okay. Now the statistician comes by and says, wow, I have this x bar. Given this x bar that I have, I can therefore conjecture that at most mu could have been behind me. If this is the x bar that I got, mu could have been behind me by this distance. It's possible that my x bar is actually on this end of the spectrum. I don't know that. But at most, my x bar can be behind mu by this amount. So for a given x bar, I can tell you how much ahead or behind mu really is. Okay. So all I'm interested in doing right now is figuring out the range within which mu can exist for a given x bar. To do that, I use the fact that mu is known. For some mu, I know the distribution of x bar. If I can quantify this distance, if I can quantify what this distance is and call that x, we won't call that x, let's call that distance y, then I know that x bar can be at most y ahead or y behind. Therefore, if for a given x bar, mu is y ahead or y behind. Okay? How do I figure out what this distance is? Well, first of all, we've decided that this is a normal distribution. Okay? So if this is a normal distribution, where does it end? So it starts at mu, but this distribution, how far does it really go? How far does this distribution go? It goes up to infinite on either side. So if I start this messy question of, for a given mu, how far can x bar be truly behind or ahead? Theoretically, the answer is it can be infinite ahead or infinite behind. So I say that's fine, but that's only if that covers 100% of the distribution, right? So I don't need to cover 100% of the distribution, right? I'm satisfied with covering some percentage of the distribution. So let's say I decide I want to cover only 95% of the distribution. So I say, to quantify this distance, just a second, I'll do some amount of erasing so it's not messy. Okay. So to quantify some amount of this distance, I say I only want to cover, let us say, 95% of the distribution. Okay? If I want to cover 95% of the distribution, how far do I need to go on either side? I need to leave out 2.5% on either side. So if I can figure out what this mark is that leaves 2.5% here, I should be set. How do I figure out the mark in a distribution that leaves out 2.5%? That's knowing properties of the normal distribution, but more generally, if I just want to know in any distribution, how far do I go such that 2.5% is left out ahead of me? area under the curve, but you have something very convenient that already quantifies this area under the curve. It's called the CDF, right? So if I want to know what leaves out 2.5% of the values above me, I can just say at what point is the CDF 97.5%? Because if you're leaving 2.5% higher than you, 97.5% should be less than you. Fair enough? So couldn't you just ask the question, for what value of x would you get a result 0.975? So that's what you're doing. You're saying for what capital F of x, what should x be such that 0.975 is left over? Okay? So once you answer that question, you'll get the value x, and whatever value x you get, does that depend on, now this capital F of x is for a mean with normal, with a mean mu and standard deviation sigma by square root of n. Correct? I'm asking what is x for this distribution, for a given mu and sigma by square root of n, what is x such that capital F of x is 0.975? Now, I am anyway not interested in x per se, I'm interested in mu minus x, correct? So this is x, this is some value x, okay? What is this value? It's mu. What I'm interested in is this distance, the distance from mu to x. So all I'm interested in is mu minus this distribution, which is nothing but a normal distribution with a mean 0 and a standard deviation sigma by square root of n. Fair enough? So as long as I find out what is x, for what value f of x is equal to 0.975 for this distribution, I should be able to come up with what that distance is. By the way, what distance am I interested in, guys? I've marked it just now. I'm marking the distance which is from mu, how far can x bar go ahead or behind, such that I'm covering 95% of the area under the curve for the distribution of sample means. Okay? Why am I interested in this? If I know how far x bar can stray from mu, I know from an x bar how far mu could have been behind or ahead. Okay? Because now you have some mean mu. You have some mu. You were interested in this point x. Now if I added 10 to mu, what would happen to x? It will just become x plus 10. You're taking that whole distribution and moving it. So the distance from mu to this place, that location, is unaffected as to where mu is. Mu can be 5, it can be 10, it can be 200. Ultimately, you're trying to get this distance. It doesn't matter where this location actually is, the distance stays the same. Right? So mu can be mu plus 10, it can be mu plus 100. Since you're only interested in this distance, right? It's literally like saying I care about the distance from mu to a point in this distribution, this f of x of the capital F of x, where the capital F is characterized by this distribution. Right? So that's nothing but a normal with a mean 0, because you've already moved, and your standard deviation is sigma by square root of n. So basically I'm saying mu does not matter. You can completely ignore mu, because you're not measuring x with respect to the number line alone. You're measuring it with respect to the distance from mu in the first place. Okay, so now we know, now the problem is we should be able to get, for this distribution, we want to get capital, you want to find out x such that capital F of x is equal to 0.975. I'll rewrite that here, capital F of x such that it's equal to 0.975. You want to know what x is for this distribution. And it turns out, well, that is not very easy, because you'll have to give me sigma and square root of n. But instead, if I just divided this distribution by sigma by square root of n, right, what I'll be left with is a normal 0, 1 square. And for that distribution, I already know what capital F of 0.975 is. Why? Because someone took this normal 0, 1 square and actually computed all the possible x values and the capital F of x values and put it in the back of statistics textbooks. Right? Somebody actually sat and did that. Now, that is what you know through this. So you've often seen it as z of 1 minus alpha by t or some z score, right? That is nothing but somebody going to this distribution and saying, oh, in this distribution, can you tell me what f of 0.975 is? And they get that value, and once they substitute the value, you're saying, that's fine. You've told me what x is for a normal 0, 1 square, but I was interested in a normal 0, sigma by square root of n. So I need to multiply the sigma by square root of n back. Once I do this, I have an x bar. I know that the distance between my x bar and mu can be only plus or minus this quantity. If it can only be plus or minus this quantity, I can figure out within which range mu should really be. Okay? Okay, so this, I've taken something very simple. I've taken the one sample z distribution and told you, I tried to explain as to the logic behind how you are really given an x bar, but your job is to say something about the interval within which mu exists. And how can you go about taking this example and figuring out where mu should exist given some value of x bar?